So 5.3, misnoted as 5.4 in your notes, so make that correction, is reviewing and talking specifically about a tangent line. So just to review, remember a tangent is a line which touches a circle in one spot. So when we are thinking about a diagram of our circle, a tangent line is going to come through like this, or it may come through like that. Okay, but it's only going to intersect in one spot. And there's a couple of key theorems that result. And the first is the perpendicular tangent theorem. In a plane, a line is tangent to a circle if and only if it is perpendicular to the radius at the point of tangency. Now that's a lot of words, but this is a super powerful theorem. Remember we talked about the point of tangency is this intersection spot. And that becomes a key spot because, notice, if and only if, so this theorem works both ways, it is perpendicular to the radius. If I draw a radius out here, and there happens to be a line of a tangent line, and they intersect at that point of tangency, this is a right angle. Now you can see why that becomes so powerful because I can start to drop potentially right triangles in. And then using the Pythagorean theorem, I can find distances and work through problems. So whenever you have a line of tangency, it is going to be perpendicular to the radius at that point of tangency. Congruent tangent theorem is equally powerful. And notice it's congruent tangents. We're going to be talking about two tangents. If two segments drawn from the same exterior point are tangent to the same circle, then they are congruent. And if you think about this picture right here, exterior point C, two lines of tangent to A and to B. They are the same length. You can see here. And you have the first theorem shown where I have right angles at the point of tangency. And since those right angles are created by radii, they are equal. And now I have a set of congruent triangles. And I can find that, or a kite BOAC, or I have congruent triangles here and here, Pythagorean theorem, I can find this hypotenuse, and you can see a number of calculations and problems can start to happen because of those two key circle theorems. So let's start work. Find A to C. Now in these problems, always be careful that you know what you're being asked. Are you being asked to find A to D, D to C, A to C? There might be multiple steps. You might have to find one length and then subtract or add. So just always be careful. But since I'm trying to find A to C, this whole length, that happens to be the hypotenuse of a right triangle, ABC, since BC is tangent, the radius there, and so AC squared is going to be equal to 5 squared plus 8 squared. Remember, hypotenuse is always opposite. So AC squared is 25 plus 64. AC squared is 89. Take the square root to find what AC is. It's about, 9.4. We don't have to consider the negative value in this case. Remember, when we take the square root, we always get plus or minus. But since AC is our length, we only need the right or the positive value. Now this next example is asking us for perimeter. Remember, perimeter is the distance around a figure. So we need to fill in some measurements here? Well, if this point and this point are from that external point tangent to the same circle, that means those pieces are congruent. This point and this point are tangent from the same exterior spot, so they are congruent. This point and this point, same deal, so that makes this 3. If that's 3 and the whole length is 6, then that means from GF and GH are also 3. And once you've used that external point congruent tangent theorem, you can simply add up the sides. And so we have a side of 7 in AG plus 12 for AC plus 11 for EC plus 6 for GE. And that ends up being 36 units. Now, at first glance, this next example looks like it might be very hard. But if you use that external tangent theorem, let's call this point W, just so that we can talk about it. W to D is going to be the same as W to C, because those are tangents drawn from the external point to the same circle, only focusing on circle Q. If I look over at circle R, WB has to be the same as WC, because that is also two tangents drawn from an external point to the same circle. And if you notice your markings, what I know now is that those two expressions are the same. And some simple algebra later, we have 8x is equal to 22, x is equal to 2.75. Now this is one of those scenarios where you have to pay attention to what you have. When I ask you to find x, here, x is this outside segment right here. So we are looking at a Pythagorean theorem problem, except it doesn't appear initially that I have all the information I need, because I only know that this outside segment is 8. This inside segment, though, I do know, because it's a radius. So the inside segment is 12. And so what I have to use for my Pythagorean theorem is the whole segment, which is 20. So always be very careful that you're using the right values and using the appropriate values for your problem. Remember, the hypotenuse is always the longest side. So if for some reason it's not the longest, you might want to check your calculations. So I have 20 squared is equal to 12 squared plus x squared. So I have 400 is equal to 144 plus x squared. Subtract 144 from both sides, so you get 256 is equal to x squared. Square root both sides, and x is 16. That works because it's less than 20, and so I know that I have an appropriate value. Now the last example, quick little typo. We're not finding TR, we're actually finding TW. At first it doesn't look like there's enough information to find TW because we're missing KW. But again, if I remember that segments drawn from an outside point to the same circle tangent are congruent, I know that this piece right here is 9.5, and so my whole segment by parts to whole, add those two pieces up, and